Thank you, Dania. All right. Good afternoon, everyone. I hope it's okay. Yeah. And it's a pleasure to be here with you today to explore a subject that sits at the heart of modern engineering innovation, which is technological advancement and evaluation of tools over the years. So for decades, I believe structural engineers have managed to navigate the gap between concept and construction. But I believe today that's changing fast. We are in a new era where intelligent automation is not only eliminating repetitive workflows, but it is reducing human error and also accelerating project deliveries. So in this session, we'll explore how the latest software solutions are integrating geometry, logic, and design in a ways that are, I would say, not only smarter, but even transformative of how we build and design. So, and yeah, personally, since I'm most familiar with MIDAS tools, I'll be using that extensively in this presentation. Okay. So these will be the contents. And yeah, again, nowadays, I believe project margins are shrinking, costs are going up, and technology is evolving faster than ever. So to cope up or to cope up with the market, I believe project delivery should be efficient. It should be within limited amount of time. And also we should be considering or be complying with the standard codal clauses. So let's understand this in the presentation. So let's take a look at the very first part, which is time optimization, and also understand how technology is evolving with understanding the advantages and disadvantages of every step. Okay. So the very first one. All right. Just a sec. Okay. So first one, UI modeling. So this is a typical way of modeling from the time where software were first introduced. This is just a UI modeling procedure within MIDAS. But I believe this might be very useful back then, but evolving technology, even this procedure had to change due to a couple of reasons. Firstly is reliance on multiple sources for a preliminary data. I guess William has mentioned material sections which to choose or which to prefer for. Second is time-intensive manual inputs if you need to modify anything, change anything, or for matter of fact, even result extraction. So for every revision, we need to extract results for every other scenarios, and it is a very time-consuming process. And it is also with UI modeling, it is prone to user oversight. It is difficult to reproduce the same results, and I believe limited flexibility with the iterations. Mainly, time is a very big constraint when we are going with the traditional UI modeling. So then, what would be the way forward with this? So we can think of Excel. Since every engineer is familiar with Excel the most, we can use of Excel as a centralized platform and automate workflows through Excel, which will help us reduce all the time which we are manually spending on the software part. So I believe this gave your idea of how manual UI modeling can be conducted within MIDAS, definitions of material, defining the entire geometry, structures, and extracting the results. And if we intend to do the design within the software, we can conduct design as well. I believe this was an example of a steel composite bridge in curved span. Select elements for design. I'll just skim it through. Yeah. Check the capacity of few sections and obtain the detailed design report from the software. Yeah. The design guide as well. Okay. So now let's see if we do switch to Excel. All right. Okay. And choose it as a centralized platform. So this Excel template is shown here is a similar example. It is a completely automated spreadsheets wherein the entire geometry section, model, load, construction stages, everything is automated. Even result extraction will be is automated in the similar workflow. And with Excel, as long as the Excel template is used for that intended purpose, maybe for the steel composite bridge with zero radius or without no skew, it works like clockwork. So we can use it n number of times. It is very efficient, very seamless. But as soon as we try to make any changes to the existing workflow, most of our work is disrupted because we need to change all the automation, check every step of what the material is created, how the geometry is changing, how the geometry is aligning with the loads which are input. So I would say for fresh models, yes, this is a very good workflow and engineers have been using for a long time. But now when there are revisions, again, if we need to add a skew or if we need to change the radius, I'm not saying it is not possible. It is a bit difficult with Excel. Now then engineers had to look for another option. So what would that option be? So it will be graphic and parametric tools such as Blender or Grasshopper. Okay. So for this video, we see entire bridge was model and the results were extracted in Excel itself and also the images for report generation and documentation. Again, this works very well for a typical bridge, specific bridges. Okay. Now we have established that for fresh models, either you go with UI modeling or with Excel workflows, it will work very well. But what if we need to add parameters? As I said, change the skew, change the alignment. Then there the parametric tools such as Grasshopper comes in place. This is a simple example of how it can be parameterized. So here we are already created the model with Excel or with UI modeling. So now we will add a parameter to change the alignment. It is obviously it is very good if you parameterize the entire structure from Grasshopper itself, but we can also use Grasshopper to add parameters to a few necessary elements. So over here, it's an example of changing the alignment. So we imported the nodes in Rhino, defined a initial curve and a final curve so that the offset reference to move all the loads and the boundary conditions are present, and then we can update the geometry. So I believe this is much more quicker and efficient with Excel. Again, I'm not saying this is a better version, but I believe engineer has to choose or which tools he has to use for a specific tasks. Okay, now limitation with such tools. These tools are easy, but this does require an urge to go beyond just the structural engineering domain. And also with commercial tools such as Grasshopper, there is a cost associated with it. So again, the accessibility is limited. Okay. Just on this, and another example of aligning or modifying the skew for the specific structure. So we have seen just changing the alignment, and just for the skew angle, we have used Grasshopper. All the manual modeling was done by the core software. So as I said, there is cost associated with it. Therefore, the accessibility for such tools are somewhat limited, I would say. What is the way forward with this? Then engineers tend to move to Python. We'll see why Python would be beneficial. Okay. So Python and why it is gaining traction. So first is versatility, and it is its integration with modern tools and APIs. And also Python, I believe in 90-95% of all the AI tools which are being developed, it is based on Python. So therefore Python is widely accepted. Obviously, it is widely accepted not only in structural engineering, but even in other domains of engineering. So let's talk about standard libraries in Python, which I believe will be the major asset for anyone who are using the libraries. So I believe everyone must have heard about standard libraries of Python, such as NumPy, Pandas, Matplotlib. These are typical libraries which are very famous. Similar to those, based on the similar concept to reduce the workflow, MIDAS has created its own Python library. So it will reduce your entire script to easily readable syntax, I would say. This is just a list of all the components of library. If an engineer requires, he can also take a look at all the backend coding of the library. It is free for, or it is open source, I would say. And for the engineers who just want to get the job done, directly use the library and do any specific changes. Okay, so just on this part, we can see this, I believe hardly 7 or 8 lines of code is written, and entire bridge structure would be generated with this. So length is specified, width, skew, and number of diaphragms. And RCC T-girder is an example over here. So materials, sections, geometry, boundary conditions, loads, and even analysis is integrated with this single tool. So we'll be in that just single line, engineer need not spend much time, just understand the code first and then generate the model quickly. And I also mentioned versatility. So how Python can be used? So it can be used to generate drawings. So instead of using any intermediate tool between analysis software and the drawing part, we can directly generate drawings from the analysis tool itself. So it can be done with the help of Python. So for the same structure, the RCC T-Gutter structure, which we generated in the last previous video, we can create a DXF format. Again, this library is Python's Python own library. We have just used those library, integrated it with MIDAS API, and the drawings will be directly generated from analysis tool such as MIDAS Civil NX. So this, I believe, will help save a lot of time in the markup drawing stage, which every engineer draws and then sends it to the draftsman, get back, make the changes, and this goes to and fro. So instead, just a ready DXF file can be shared to the draftsman. All the plan view, element details, sectional details, everything can be extracted from an analysis tool. Yeah. So we can see rebar annotations, reinforcement details. Yeah, complete thing. And yes, so I believe we have had clients who are using the AI or API until this point with Python. But then how should we prepare ourselves for the future? Yes, AI is something which is very big. And as William rightly said, I don't think so anyone will be able to cope up with it. But MADAS is trying its best to implement AI in this drawing process, in its software products. So this is just an example of what we are working on. So we are calling this as LDM, meaning large drawing model. So once this is ready, engineer can simply open the required drawings. So typical procedure is if we have a past similar project, we open those drawings, take reference of those drawings, replicate it for a new project, modify, and then create drawings again for the existing project. So this tool will be able to identify all the sectional details, dimensions, material details, and it will be able to generate an entire analysis model within MIDAS 7x. So it will read all the components from the drawing format. So all the information, general arrangement drawing, dimensions, material properties will be extracted, and a complete model will be generated in Civil NX. Then you can do manual changes, add parameters, use Python, Grasshopper to modify as per the own project, and then automatically generate drawings again from the analysis tool. So engineer need not have multiple softwares. He can just use single model file for model generation, drawing generation, and all the things. Yeah. And this is another aspect of how AI can be utilized. This is just something which we are trying on with help of prompts. So let's see how this gives an idea. So we can provide, we will be able to provide prompts. It is not developed yet. It is still development. So yeah. So a prompt to create a frame structure. We just specify what base, height, width should be provided. If you need to save, just write save the model, the folder location, and the model will be saved at the respective location. Just another example in this tool is to create a grillage. Again, this was just the conceptual stage, so just limited training. But we can see how prompting can be one of the use case, how AI can be implemented with the softwares. So create a grillage of so and so length, width, spacing, and a skew, and a grillage model would be generated. And just to give you a bit more of an insight of how everything will work. So I think it will be up ahead in the video. And yeah, so basically a Gwen 3 1.7b model, yeah, this one was utilized as an AI to generate the scripts, and anything LLM was used to train the AI on the MIDAS library. So this is how on the back end it will work. So we just, in the prompt, we're just switching the span lengths from 20 meters to 50 meters and click on generate. It will generate an entire Python code, and this Python code is backfed to the software with the help of API. So this is how the entire prompting function with AI and MIDAS Linux will work. All right. So Improving efficiency is always, I believe, what everyone strive for. But as I mentioned, it should not be at the cost of compromising any codal compliances, accuracy, and local industry practice. So now let's take a look at how MIDAS helps us align all of these things together in the second part of the presentation. Okay. Now in this slide, I've included all the NG specific features or which are favorable by our clients over here. So I think we are all aware that construction staging is one of the very powerful feature of the MIDAS. We can simulate every stage of construction and accurately capture the material effects or time effects, be it creep effects, shrinkage effects, compressive strength effects. So again, as per standard NZS bridge manual, these are available within the software tools. Next up are the NZ standard local sections. So these are mainly the precast sections which are widely used locally in New Zealand. Super T, iGirder, Hollow Core, or Super HI. Super HI, I believe it's a new and upcoming section which will be widely used in the New Zealand region. And also tendon automatic generation for all of these sections is already present in the software. Next up, so non-linear boundary conditions. So especially in New Zealand, as opposed to Australia, where the linear conditions are used, in New Zealand, the non-linear functions are used to represent soil structure interaction. And yes, it is a very time-consuming task. We receive the properties of these nonlinear functions in Excel sheet. Then we define the graphs first, and then we define the springs at different levels of the structure. So now for such scenarios, and automation is already in place. Let us understand how this automation will work like. So left hand side is a basic bridge structure, and on the right side Excel sheet where the force deformation functions are present. It will be a two-step process. First, to import all the graphs of nonlinear functions into the software. So we can see all the graphs are imported. I believe there are 25 graphs. Yes. Step one, and then step two is to assign the functions at respective depth through the soil and also generate the piles as well. So a reference node is provided such that the reference for the specific locations of the spring can be determined. Top nodes from which the piles will be created are selected. So we enter the same information in Excel. And then section ID and material ID. So which sections and which materials to be assigned to the piles which will be created. And once this is all set, we can simply click on create piles. And one by one, all the piles will be created, and also specific force deformation functions will be assigned at respective depths. So all the revisions you have can simply use this function, n number of revisions, multiple springs, even if they are obtained n number of times, we can keep using this functionality as is. Next up, so standard NZ vehicles. So all the vehicles such as HOHN, general access, 50 max, fatigue vehicle, deck evaluation. These are all the vehicles which are available in NZ bridge manual. These are all a standardized option within the software. To go into more specific, every vehicle has a particular tire area. So usually in plate elements for bridge deck, if we consider a area load rather than a point load, we obtain a better force distribution. So that also can be considered within the software. So we can obtain a moving area load instead of a moving point load for plate elements within the tool. Also, the next one with moving loads is the dynamic factor. I believe this is very unique to NZ, that for every output of moving load, be it positive movement, negative movement, shear force reaction, there is a different factor associated with it. So even for an element which is going into positive and negative movement for different load case, for a single element, there is a different factor. So again, that also has been considered within the software, which has been automated, I would say. So all the outputs with all the respective factors will be considered and the result will be obtained. Next up is response spectrum. Yes, this is again a direct option. Select the soil, maybe probability factor, other parameters, generate the response spectrum curve and use it in the analysis. But the main challenge is combining the response spectrum and the soil nonlinear function. Response spectrum being a linear analysis, it cannot be utilized directly with the nonlinear property which we have defined in the soil. So for such scenarios, we have developed a tool which is, we named it as iterative response spectrum. So let us understand how does this work. And this follows a similar procedure which we have discussed with the clients in New Zealand. They used to do this manually, but now a tool has been developed for such purpose. So whenever a nonlinear function is assigned for the bridge and we conduct a response spectrum analysis, all the nonlinearity is converted to linear spring, considering the initial stiffness. Once it is analyzed, a displacement is obtained at each and every spring location, and we assume a particular tolerance. If the displacement is outside our assumed tolerance, then a secant is drawn from 0 until that displacement in the nonlinear function. Now a reduced stiffness is obtained. And again, response spectrum analysis is conducted. And this has to be done repeatedly so many times that all the nonlinear springs in the model should be converged within the tolerance limits. So we understand that this must be very time-consuming process. So again, a tool has been created in this place for such scenarios. So we can see the same structure which we have been seeing in this presentation. There are nonlinear functions. This has been developed with Python. So when we execute the ITR, iterative response spectrum script, it is using a boundary change assignment feature because that stiffness has to be just used for the response spectrum and not for the static cases. Tolerance is assumed. Again, obviously a playback speed is applied to this. So, but we can see a live convergence graph as well, and the spring values which are updated at every iteration. So in each iteration, software is comparing all the spring location with the tolerance limit, updating if outside tolerance limit and putting it back into the software. So around, I would say 12 iterations were conducted, and then the software has finally converged. I believe manually it would at least take a week for such updation and iterations. And also a debug log in Excel format of what are the steps, what are the maximum tolerance at each step is observed. Okay. Another typical analysis which have been observed in Australia and New Zealand. In Australia, again, it is a linear analysis, but in New Zealand, it is non-linear springs. So it is called as soil sensitivity analysis, wherein we already have the soil nonlinear functions. Let's say they are of 100% stiffness. Then a different model or different case is created where the stiffness or the P, so force deformation, the F is reduced to 50% value divided by 2, and a third scenario where the F in the force deformation function is multiplied by 2. It is increased to 200%. And a sensitivity analysis between all three models is conducted, and the results are compared, and it is designed for more critical values. So again, this has been automated within the tool. Let us understand how this work. Again, same structure where multilinear springs are present. Let's look at the inputs first. So scaling percentages, we want to scale it to 50, 100, 200. ITR specifies it should go through iterative response spectrum analysis, AN just regular analysis. Name of the model and the location where the model is saved. And for result extraction, the load case, structure group, and the support groups whose results need to be extracted. So when we execute the ITR script, first step is to create the different cases where the spring stiffness are scaled to 50%, 100%, and 200%. So step 1, create models with different scaling percentages. So it will create, and the first one, the 50% scaling was set to ITR analysis. So the iterative analysis which you have seen in the previous present slides is being conducted over here. So it will also give you a detailed overview of what are the displacement tolerance and the terminal view of the Visual Studio. After the analysis is complete, as it's converged, then it will automatically extract the result and save it in an Excel sheet in the background. Then next up, it will open the second model. So all of this with a single click, it will be conducted. Second model, SSA underscore 100. It will be analyzed, and also its results will be extracted in an Excel spreadsheet. You can see the UI of the software changing because it is actively extracting the results from the software into the spreadsheet. Yeah. And finally, the last model, which is SSA 200, It will automatically open that model, analyze it. So there can be multiple models. These are just three, but if you want to test the sensitivity for different scaling percentages, 75, 125, you can add multiple models, and all of these models will be analyzed, scaled, and results will be extracted with a single click. All right. Script summary of what are the extraction procedures. If there is an error, it will also give an error that this is the error, please change this. And finally, we'll look at the Excel sheet, where the script has been compiling all the results. So all the three results, 50%, 100%, and 200% scaling, are compiled in one Excel sheet. These are the beam force results, then the displacement tables for all three models. So we can compare, and uh, in a single view, we can have a glance of what are the results, different models. And also result images are also extracted in Excel spreadsheets. All right. Yep. So this was about soil sensitivity analysis. And next one, just very brief about this part, pushover analysis. There are also going to be a demonstration of pushover with building structures. So maybe we'll understand more about pushover in the next slides. Then just to show that this is also a functionality within the tool, which is dynamic nonlinear. If you want to maybe specify a base isolator, shock transmission units for our structures, yes, that can also be conducted within the tool. And the inelastic time history analysis, I believe most advanced seismic analysis, uh, it is also possible within the tool, also with fiber hinging. So either we can use fiber hinging or moment curvature or rotation kind of hinge properties for the model. And yes, so to sum up my entire presentation, I believe traditional methods will always be there, but as engineers, we want our tools to build design faster, safer, economical, and also optimized. So yes, automation is something which was considered fancy in the past, but with all the resources which are available lately, it's on all of them being just a click away. We believe it is something easy and easily achievable. And yes, for all this, we at MIDAS are always there to help you at every other stage. So not just yet, I might continue with my next one. Yeah. So this is a short bit, maybe about 10 minutes, with simplifying seismic analysis for buildings with MIDAS Gen. So this is just to give an idea, because I believe MIDAS is very well known in the bridge industry space, but just wanted to highlight the building side of MIDAS, which is using MIDAS Gen, and pushover analysis or seismic, which is very required in most of the projects in New Zealand, just to demonstrate the capability of the pushover side in MIDAS Gen. So I believe this is the typical workflow whenever we need to conduct pushover or performance-based design, I would say. First step is to assume a particular section size, then assume all the material sections and so on. Then we either, if we use response spectrum analysis, then go through that ITR iterative analysis to obtain a demand compatible secant stiffness. Then we design the particular section, and then we go for the pusher analysis to check the particular performance of a structure. If the performance is satisfied, all good. Otherwise, we need to resize all the sections, redesign, and repeat the entire process again. So not the entire process in the demonstration part, just the last step of pusher analysis with the building structures. I've considered an example. So just it will be, I believe, a 5-7 minutes video. I'll explain through the video. For those who are familiar with civil, I believe this is the same interface of civil, but just all the functions are for building specific. The UI, tree menus, unit systems are all similar. So there should not be much time to get hands-on with the tool. Just to give basic information about the model, materials, sections, loads are defined. So there is also a shear wall considered, model with automatic meshing feature within the tool, and some basic loads, earthquake loads, wind loads, and response spectrum as per one of the scenarios of the NZ code. So it is already analyzed, and we'll first look at the mode shapes, because in pushover, it usually depends on what kind of pushover load we are going to apply. Either it be a nodal body force, inertia force, or just a specific fundamental mode, either X, Y, or Z direction. So I think with the modal shapes. We have already determined the fundamental mode for X and Y direction. Then we'll start defining the pushover controls one by one. First with the global control. If there are any permanent loads, there would always be some permanent loads. So the permanent loads should be added first in the initial control. So after the deformation of the permanent loads, then the pushover analysis should be conducted in the deformed state of the permanent loads. Then set up some necessary options in the global control. So step 1 done. Step 2 is to define the pushover cases. So we defined 2 pushover cases, push in X, I believe LCX and LCY. Set up the iterations P delta. Either we go for P delta or large displacement, which is geometric nonlinearity. Load control or displacement control method. I guess those are already familiar with civil. Most of the steps are similar, but this is mainly for the engineers who are working in the building sector. And then for the control node, we specify a particular node at the top of the structure, specify the maximum displacement at which the pusher should be restricted, and different load cases or different options to apply push load. So here we are considering mode shape. Mode shape 1 was very dominant in X direction, and for Y direction, we also set up similar push case. So I believe mode shape 2 for Y direction. So this completes the second step, is to define the loads for pushover. The next one would be to define the hinges. So in hinges, there are different types which engineer uses, be it moment rotation, moment curvature, either lumped or a distributed moment curvature, and also fiber type of hinge. Then we have different interaction types, PM, PMM, or none. So when defining the pushover hinge for beam elements, usually MY, and different types of hinges, skeleton curves, bilinear, trilinear, or as per FEMA and Eurocode 8 standard are automated within the tool. And yes, if we have a specific skeleton curve, there is also an option to user define a specific skeleton curve within the options. Yep. This is for beam elements. Then for column elements, usually the PMM interaction type, because actually it's very dominant. So we go for PMM interaction type for hinge for a column. So we'll just define that. So fx, my, mz, all of these degree of freedoms are considered for the hinging, capable of hinging. And finally, wall elements. So wall, which is modeled as a plate element, will define that with setup of a fiber model, just to explore the possibility that yes, fiber modeling is possible. And in this, we believe we can see how convenient and easy it is to specify a fiber model to the building element. So import the existing wall element, then we mesh the wall element with equal sizes, or we first define the materials. So different material models are directly available. For concrete material model, I believe Japanese code, Mander model are available, or there are a couple of models over there. We'll just select the Japanese one for this one and specify the materials. For concrete, similar materials will be defined for steel. Again, couple of options for steel out there. Menon, Ghetto Pinto, and various others, Japanese code. And yeah, specifying the steel properties. Yeah, and then set up the entire fiber hinge model. This is just the concrete part. After defining the concrete fiber hinges, we will define the hinges for the reinforcement as well. Since this is already a designed wall element, all the reinforcement which is already designed will be imported into the same fiber hinge section. And yeah, so this completes our tedious process for the hinge definitions as per fiber model for wall. Again, the skeleton curve for the same is also there. And then after this, yes, we simply run the analysis. So pushover analysis. Oh, yes, we have to assign those hinges we have created. So for beam elements, then column elements, interior columns, exterior columns. and finally for the wall elements as well. Yes, after we assign the hinges, let's run the entire pushover analysis for both the scenarios, push X, push Y. And while it is performing the analysis, we also get to see a live pushover graph that is being generated over there. Once the entire pushover analysis is conducted, so for both the scenarios, X and Y. Yes, so this is the global pushover curve. And yes, if we need to obtain the pushover curve for any specific elements, that is also possible. So after pushover curve, we need to determine the performance point. So yes, for performance point, we can select the respective options. As per FEMA 440, there are 3 procedures of how pushover point can be calculated. And also as per ATC 40, which is closely related to our codal standards, we can use that procedures for the performance point. And yes, also observing the hinges or how the hinges are developing through the entire steps of pushover can also be observed. So the first step where all the hinges are linear, then we can see some turning into green, yellow, and then red. So different steps, IOLSCP, yeah, where hinge failing, and also yes, animated view, so we can see the progressive hinging of the entire structure within a single view. And I believe that's okay. The last part, it also obtained the pushover or force deformation or moment curvature curves for specific elements, as well as for the fiber hinges for the wall elements. Detailed fiber hinge results for every fiber hinge in the wall element. And yep, with that, I would like to end my presentation, and thank you so much for listening. I hope it was an interesting one. Thank you.
Thank you. Just hold there. We've got a couple of questions from online, and then I'll ask if there's any in the room.
Where can we get the plugin for the calculation of PY curves?
You can mail us ausupport@midascity.com and we will send it to you.
Awesome. For beginners learning MIDAS, is Python knowledge required? I was also wondering whether the Python codes and Excel files demonstrated are automatically created by MIDAS or if users have to develop them manually.
So all the things which are developed by MIDAS, which are even showcased in the presentation, will be sent to all the users who are attending the session, or else you can also request us. And all the scripts within the software or with the external tools are open source. So you can take the script, learn the script on your own, and yeah, develop your workflows. Thank you.
So do you need Python knowledge?
Not to learn MIDAS, yeah, that's the right one. But yes, if you want to develop workflows, it is not mandatory, I would say. And we are also helping engineers. In fact, next month we have a training session we are using Grasshopper, VBA, and Python. So maybe the interested engineers can join the training sessions and experience themselves how Python can be utilized and how minimal inputs are required for your workflows. Thank you.
Any other questions in the room? No.